33.84? Yeah, 33.84, which would round to 33.8%. So this is percent by mass. One thing I'd add is the units here. They didn't put the unit percent, but I always do. Percent. Well, I always do put the unit because this composition for fairly concentrated solutions, what happens if we have a very dilute solution? If we have a very dilute solution, then we might not want to use percent. So for example, if it's fairly concentrated, let's say 1 part out of 2 is A. So just as an example over here, if we do 1 out of 2 parts is A, then 1 part A out of 2 parts total. This is what we call a fraction. So this is the fractional composition. We could write this as a decimal here. A decimal would be 0.5. The decimal is actually a fraction as well, because this is 0.5 out of 1. And so 0.5 parts out of 1 part. It's just the decimal is just written per 1 rather than per whatever we got. And so this in this particular problem is per whatever we got, and what we got total was 42.3 grams. And so for fairly concentrated solutions, we'd use this, but we'd convert this into percentage because percentage is a little easier sometimes to read. So 0.5 times 100% gives us 50% A. And so this particular mixture is just 50% A, 1 part out of a total of 2 parts. But let's say it was significantly more dilute. So rather than 1 part out of a total of 2 parts, let's do 1 part out of a total of 20,000 parts. And so this is very dilute total. And so 1 part of A out of 20,000 parts, this would be 10 to the minus 4. Minus 4 to the 10 to the minus 4. 0.005. And so this will give us a decimal. So here's our fractional composition. Here's our decimal composition. And then we times this by 100% to get the percent composition. And so we times it by 100%. It's only going to move it 2 decimal places. So this is going to come out to 0.05%. That's okay. 0.05% A we can deal with, but sometimes that's not as convenient. Sometimes it's more convenient to use other units. So for example, if this were 0.05 liters, rather than saying 0.05 liters, we might just say what? Sometimes it's not as convenient. If I have 0.05 liters, can you visualize 0.05 liters in your mind? It's hard to visualize 0.05 liters because that's a tiny fraction of a liter. But it's probably easier to visualize 50 milliliters because 0.05 liters is 50 milliliters, right? And so 50 milliliters, you can immediately kind of visualize what 50 milliliters looks like versus what 0.05 liters looks like. But they're the same thing. 0.05 liters and 50 milliliters is the same thing, right? And so this is in preparation for the final because I talked about this near the beginning of the semester. And, rather than multiplying by 100%, we might try a different unit. And so this is parts per 100. And so what other units can we use? Just rather than using liters, we might try a different unit like milliliters or microliters. In terms of microliters, how many microliters is this? This is 50,000 microliters. Well, 50,000 microliters, it's kind of hard to visualize maybe as well. But these are other units that we can use. Well, we don't always have to use percent because sometimes percent's not the most convenient unit. And so for something like this, 0.05%, yeah, maybe it's okay, maybe it's not. What other units can we use? What other units are commonly used? And so rather than multiplying it by 100%, we might try to multiply it by a million, but we don't call it a percent, we call it a parts per million, or ppm. So in terms of ppm, what would this be? Well, 1, 2, 3, 4, 5, 6. This comes out to 500 ppm. And so 0.05% is the same thing as 500 parts per million. We probably don't want to go parts per billion because it would be 500,000 parts per billion, which is not as convenient, right? And so we pick the unit depending on what the composition is. And so, for example, the composition of CO2 in air is what? The composition of CO2 is 0.032% CO2 in air. Well, 0.032% is probably not the most convenient, although it's convenient in the sense that everything's given as percentage, so you can see that this is very small, you know. But 0.032% means that we have 0.032 out of 100. So for every 100 parts, for every 100 atmospheres, we'll have 0.032 atmospheres, something like that, you know, or parts. But what if we did this in parts per million? If we do this in parts per million, then we'll just move the decimal over. So this is 0.032 out of 100. And so let's go to million. So let's move the decimal over. How many more do we need to get a million? One more. We'll move it 4 places over. And so what this comes out to is this comes out to 320 parts per million CO2 in air. Do you see that? So 320 parts per million. Well, 320 parts per million, to get it back into fractional form, it's 320 out of a million. To get percentage into fractional form, we just divide it by 100. To get ppm back into fractional form, we divide it by a million, rather than 100. And so we talked about this earlier, but percentage is very common, as is parts per million, as is parts per billion. All of them are the same, just different. You know, percentage we multiply by 100%. Parts per million we multiply by a million, the fractional or the decimal. And to convert back into fractional, we'll just divide it. So this converts it back into fractional. Okay, here's another example of a calculation. You are to prepare 250. This is all sometimes done. We want 3 sig figs here, so they just said 250 grams. It's a little bit ambiguous. 250 grams might be 2 sig figs or 3 sig figs. One way to avoid that ambiguity is to just put a decimal. So, but sometimes you'll see is people will do this: 250 decimal grams. And then you take that as 3 sig figs versus 250 grams. 250 grams might be 2 or 3 sig figs, or it might be infinite or infinite if it's exactly 250, you know. And so it's a little bit ambiguous here. And then here they're writing in scientific, but it takes up so much space, 2.50 times 10 squared grams. But there it's totally unambiguous. It's going to be 3 sig figs. Of 7.00% by mass sodium carbonate solution. And so what we need to do is we need to go from a percentage to fractional, you know. And then the same thing with ppm or ppb, you know. If it's 7.0%, then that means 7 out of 100. If it's 7.00 ppm, then that means 7 out of a million. And so it's the same type of process. The percentage, ppm, whatever we're dealing with, we should be comfortable doing any of these. And so this is 7.00% by mass sodium carbonate. And so what that means is we must have 7.00 grams of pure sodium carbonate per 100 grams of total. The total is the solution or the mixture, so this is going to be sodium carbonate solution. So in 100 grams of sodium carbonate solution, we have 7 grams of sodium carbonate. That must mean we have 93 grams of water. What mass in grams of sodium carbonate and what volume in milliliters of water do you use? give us the density of water here. And so what we want is we want 250 grams of sodium carbonate solution. So basically what we'll do is we'll just use dimensional analysis for this. And so we need something that gets rid of sodium carbonate solution. Well, we have it right here. What gets rid of grams of sodium carbonate solution? The percent mass here. Let's go ahead and do that. The 250 grams of sodium carbonate, and we have 7.00 grams of pure sodium carbonate for every 100 grams of sodium carbonate solution or mixture. And sodium carbonate solution consists of pure sodium carbonate mixed with water. So this would be, again, 7 grams of sodium carbonate, 93 grams of water. So grams of sodium carbonate solution cancel. That gives us pure sodium carbonate here. So what mass in grams? Now we're done. So what is this? Well, for every 100 we need 7, so 200 will need 14, and then half of 7 is 3.5, so we're going to need 17.5 grams of sodium carbonate, pure sodium carbonate. Now, for the grams of water, we have 2 ways of doing the grams of water. 1 or 2. Yeah. 2 ways of doing it. Way 1 we could do this is this. If I have 250 grams of sodium carbonate solution, then I know that, well, if it's 7 grams or 7% sodium carbonate, it's got to be 93% or 93 grams of water, because it has to add up to 100%. So 7% sodium carbonate, 93% water gives us 100%. And so this is going to be 93.00 grams of water for every 100 grams of sodium carbonate solution. And so let's see what this comes out to. Here, maybe 250. Times 93 divided by 100. 232.5. Or 2. 2 is just this. You know, the grams of solution equals the grams of solute plus the grams of solvent. And so how many grams of solution do we have? We have 250 grams of solution. How many grams of solute do we have? We have 17.5 grams of solute. And the grams of solvent, we don't know. And so we just solve for grams of solvent. Grams of solvent equals grams of solution minus the grams of solute. And so that would be 250 minus 17.5. So the grams of solvent comes out to 232.5 grams of water. Well, water is 1 gram per milliliter, and so this comes out to 232.5 milliliters of water. Same thing, 232.5 milliliters. Let's see how they did it. The first part is they just used some dimensional analysis, calculated grams of sodium carbonate, realizing using the fraction. For percentages, we convert those into fractions. For ppm, we convert them into fractions. For ppb, we convert them into fractions. These fractions are used in dimensional analysis as conversion factors. Okay, next they're using method 2. The grams of solution here is equal to the grams of solute plus the grams of water, or solvent. Solve for the grams of solvent is equal to the grams of solution minus the grams of solute, which gives us 232.5, which rounds to 233 grams of solvent. Okay, we're out of time, I think. And so what we'll do is we'll continue this. Actually, we don't have much left in this chapter to cover, I think. Or maybe, let me take that back. We do have a lot left to cover. We'll continue there. Next week we have another test, though. We'll start talking about preparing for that and also preparing for the final.